Welcome. My name is Nicodemus Ongeri, your lecturer at Shani Professional College of Science and Technology. Today, I'm taking you through the Advanced Internet and Core Computing Certification course, Module 2, Data Representation Number Systems. Previously, we had looked into the basics and introduction of data representation. Now today, I'll be based on number systems. Human beings use decimal base 10 and duodecimal base 12 number systems for counting and measurements, probably because we have 10 fingers and 2 big toes. Computers use binary base 2 number system as they are made from binary digital components known as transistors operating in two states, that is on and off. In computing, we also use hexadecimal base 16 or octal base 8 number systems as compact form representing binary numbers. Let's look into decimal base 10 number systems. I've talked of base 10, 12, 16, and we have 8 here. So let me look at base 10. Base 10, decimal, this is decimal, base 10 number system. In decimal base 10 number system, it has, or rather we have 10 symbols, that is 0 to 9. They are called digits that uses positional notation. That is, the least significant digit, the rightmost digit, is of the order ones. The second rightmost digit is of the order tens. The third rightmost digit is of the order hundreds, and so on. For example, I have got this number 735. When we, based on the argument under decimal base 10, we have 0. This is positional notation: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Positional notations here from the rightmost: 0, 1, 2. When we are converting it to under base 10, that is 7 times the base 10 powered by the positional notation 2, power 2, plus 3 times the base powered by the positional notation 1, plus 5 times 10 powered by the positional notation. So whatever you get is the conversion you've made from this decimal to binary. Now, let me take you to, okay, this is how we are going to represent this. For example, you might get something of this kind: 1, 1, 0, for example. Then you write to base 2, or you write B ahead of it, meaning that you have converted from decimal to binary. This is standing for bits. These are the number of bits you found out after the calculation. Let me not get to here. Let's get to something else. Number 2, binary base 2 number systems. Let's be consistent on this. Binary number systems has two symbols, zeros and ones. They are called bits. It's also a positional notation. For example, we have got this number 1, 1, 0, 1, 0. Then we have B is this notation for bits. Whenever we want to convert this, remember we are talking of the binary base 2 this is binary base 2 number system. Base 2 number system. So in this case, we are going to convert this using the same positional notations. That is, from the rightmost, we assign this 0, 1, 2, 3, 4. So we get 1 times the base 2, powered by the positional notation 4, add, just as we have been doing the rest from above. You proceed. This is 1 times the base powered by the positional notation. We are done from 4 and we are at 3. Now powered by 3 in brackets, and add 0 times 2 powered by the positional notation. Add 1 times 2 powered by the positional notation. Add 0 times the base powered by the positional notation. Whatever you get is under base 10, because you will be converting this binary form to decimal form. Number 3, the octal base. But before I get to the octal base, we shall denote binary number with a suffix b, as I have said earlier. Some programming languages denote binary numbers with prefix OB, e.g. the OB I might denote and say OB. This is from 0 bits, that is 1. Yes, then I denote. Or I might use the prefix, this is the prefix and the suffix b, this is the suffix b. I might use the prefix 0b as well. So the only thing that changes here is to add, for example, that 0 to make it the prefix as well. So let me say this. Binary digit is called a bit. 8 bits is called a byte. Why 8-bit unit? Probably because 8 is equal to 2 cubed. 3. Octal base 8 numbering system. The octal number system is another type of computer and digital based number system. The octal numbering system is very similar in a principle to the previous hexadecimal numbering system, except that in octal, a binary number is divided up into groups of 3 bits, with each group or set of bits having a distinct value of between 0 and 1s. That is, this is what I mean. We are moving from binary to octal. From binary to octal. We have said in octal it takes number systems of 0 to 7 to have 8 base, octal base 8. So 0 to 7. Then it considers the sets from this way, either 3 bit numbers and this 3 bit zeros and 3 bit ones, of which when you calculate here you may get that it is 4 plus 2 plus 1, which is equal to 7. So 0 is not there, it is on the common. Now I want to say this. Octal numbers therefore have a range of just 8 digits, that is 0 to 7, making them a base 8 numbering system, and therefore Q is equal to 8. Lastly, hexadecimal base, that is base 16 number system. This is hexadecimal base 16 numbering system. Consistency class. Hexadecimal number system uses 16 symbols, that is 0 to 9, add alphabets to surmount to 16. A, B, C, D, E, and F. They are called hex digits. It's a positional notation. For example, this is what I mean. We have got A, 3, E, then we add the symbol for hexa, which is H. Now, you've been told to convert this. What should you do? From 0 to 9 and A stands for the value of 10. So we have 10. 3 is 3. Then E stands for the value of 14 from the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So when you look at this, for example, A, B, C, D, E, F. So in this case, this is 10, 11, 12, 13, 14, 15, 16. And now E is of 14. It means FGH now to 16. Now, according to the value, in this case, I want us to do the conversion. So we are not going to multiply A times the base. No, A is a simple. We want to use values like 10, 3, and 14. For instance, this example goes this way. It is 10 times the base powered by the positional notation, that is for example 0, 1, 2, powered by 2. You add and so forth, just as we have done the rest of the things. Now, let me say this. We may be working on conversions from hexadecimal to binary. Conversions from binary to hexadecimal. It is the same story. So, and from binary to decimal, decimal to binary. So the story goes on and on. So the rest of the works that may be given depends on the student to work out correctly to present the work as expected. Thank you so much. Goodbye.